speaker tonight, Todd Michael Bailey, is going to be talking about a topic which I have clearly demonstrated I know nothing about and strongly need to be lectured at. I booked Todd Michael Bailey because a great authority had described him as a hunk, dreamy, and a fucking genius, which I feel like is the trifecta of qualities you look for in a lecturer. So again, not even knowing what the hell he was going to talk about, I wrote his name right down. And so now, the lecture that I have been yearning for, Semiconductors, and Mr. Todd Michael Bailey.
That's the nicest piece of objectification I'll probably get tonight. So yeah, my name's Todd. You don't have to use my middle name or even my last one. I want to talk to you guys tonight about a history of semiconductors. Many of you probably, if I say the word semiconductor, how many of you have any idea what that is? A lot, actually. Well, that's good. At first, I had written the blurb up here, a history of semiconductor technology, why it's cool. And then I was like, no, let me be more evocative than that. I can draw a weak parallel between semiconductors and green eyeshadow and a strong parallel between semiconductors and magic sand, because that's basically what it is. But I'm going to start out by defining for you in a loose and layperson way what a semiconductor is. And then the rest of the lecture should hopefully convince you that they are cool and maybe related to green eyeshadow and definitely related to magic sand. A conductor, probably most of you are familiar with the idea of, all right, some caveats I guess before I start. I'm an engineer, I'm an applications engineer, which means that I make stuff. Like I worked in the toy industry for a while, I designed toys and I designed motor controllers and that sort of thing. So I work with small bits of magic sand and technology regularly, but this lecture is going to be about a lot of device physics. It will probably require you to remember just the tiniest bit of high school chemistry. And that's stuff that I'm real shaky on. So if any of you find that I'm saying something incorrectly, please feel free to immediately correct me. B, if I start to talk about something which is not clear to you, or I use a technical term that you have no idea what it means, please feel free to be like, like, I don't know what voltage is. Because otherwise the lecture won't mean anything to you. And the whole point of this isn't for me to just recite a meaningless poem. It's to talk about something which I think is important and cool, and like everyone to leave with the maximal amount of understanding of that thing. All right, so caveats aside, what's a semiconductor, right? I'm going to get into much more detail about what that is later in the lecture, but to start, all of you have used an extension cord, right? An extension cord is a great example of a conductor. A conductor is a thing which does a good job of making electricity go from point A to point B. Any given wire that you use in your house is a good conductor. Most metals are good conductors. The opposite of that, if you remember from back in the day, is an insulator, right? So if you try and connect the bulb in this with a copper wire, the bulb will get bright like it is now. If you try and connect it with a chopstick or a piece of wood, it will not get bright. A semiconductor is exactly where you think I'm going with this, which is it conducts not as well as a piece of wire, but better than a chopstick. So why is that important? Why is that not just straight shittier than a wire? And the short answer to that is because you can control the amount of conductivity that it has. Any of you who have ever adjusted anything with a knob understand the idea of being able to vary a thing with another thing. You can vary the volume of your stereo by turning a knob. A semiconductor is how that happens most of the time, which is neither here nor there, but it serves to illustrate why that thing is important, right? Like if you connect your speaker with a chopstick, your speaker will be off. If you connect your speaker with a wire, it will be on. Sometimes you want to vary that volume. That's a poor analogy, but that's where we're going to start with why is a semiconductor sort of important. All right. Why do you care what a semiconductor is? You care what a semiconductor is because it's fucking everything, right? A semiconductor runs almost everything that lights up that's not a light bulb at this point in history. Any piece of electronics that you use has at least one semiconductor in it, and usually millions, right? So any of you who have used a computer or a radio or a car or the World Wide Web or any other piece of electronic arcana that you can possibly think of, any of you who have a personal piece of electronics on you have millions of semiconductors on your body right now. And that's sort of why you should care a little. There's that old saying, this is deep digression at this point. There's the old saying that any sufficiently advanced technology is indistinguishable from magic. And so this is an effort to either unmagic that stuff or make it seem like that much cooler magic for you guys. So that is why you should care. Another thing that I want to start out talking about is when people think about technology anymore, when someone talks about a technologist, a lot of the time what they're talking about are computer people, are people who write computer programs or deal with the way that you interact over a network, or generally, like technology has come to the point where you use it to instigate lots and lots of different interactions with people, and it's pretty esoteric, right? The idea of what technology is good for is real hard to pin down at this point, and what I would like to talk about with respect to semiconductor technology is that it's actually more like some 2001 shit where you make a phone club than it is like using Facebook. So semiconductor history is the coolest parts to me about the history of semiconductors are the histories of materials sciences, right? Like not that long ago, brilliant minds were poking at a rock with a wire, and now you have an advanced phone in your pocket, and the poking at the rock with the wire part is the part that's sort of cool to me. So I'm going to start out by talking about materials history a little bit, right? The reason why people have things like enormous cities and society has a lot to do with advancement in technology, right? A good example is metallurgy. Semiconductors, I'll end up talking about metals some because they're totally important in semiconductor technology and in general making microchips and stuff. But they also serve to be a useful parallel to semiconductors, right? People discovered copper around 4000 BC. Copper was discovered, some people believe, when people were trying to figure out green eyeshadow. They're the same compounds that you can put on your eyeballs to make them green also have little tiny bits of copper in it, and so there was this byproduct that people were like, oh, there's this weird goofy metal in here, I guess I can probably use that too, but what I'm really interested in is makeup. It took 1,000 years. It took from 4,000 BC to 3,000 BC, 1,000 years. The difference between now and pre-Battle of Hastings, like I can't write, I live in shit, there's no such thing as technology at all. It took 1,000 years for them to figure out that, wait, you can make these little flecks of crappy metal into anything, period. 1,000 years. It took another 1,000 years, the history from like the birth of Christ until now, 2,000 years, for people to figure out that you could actually, you could work hard on this stuff, right? Like you could beat on it, you could apply heat to it, and you could make it into something. And at that point, people got into the Bronze Age. People figured out that you could take you could take copper, you could put it into a big pot, you could throw a little tin in it, and then it was way easier to work with, it got way harder, and you could make spear points, and you could dominate your neighbors. And that was when technology really took off. Around 1000 BC, people figured out iron, another 1,000 years. They were like, oh, there's this other stuff, there's a ton more of it. And if we just figure out how to make this thing called a bellows, we can make fires that are hot enough, we can melt iron, and then we can totally dominate the shit out of the people who have bronze. And the reason that I bring this up is because that whole process, where you could make like a dirty bronze club, took 3,000 years, from eyeshadow to gnarly bronze club. And that's important, right? Because when you talk about semiconductor technology, the time span is much shorter, and the developments come much faster. And that in and of itself is a totally fascinating thing to me. In that it is also a materials sciences problem. It's also people basically screwing around with impurities and having a crucible full of stuff that they put other stuff in and being like, damn, that didn't work, and then trying something else. All right, so enough talk about bronze. Semiconductors. The concept of the semiconductors, I mean, you can't really start to talk about semiconductors until you can talk about science, right? And science wasn't really science. Like, people weren't totally sure that diseases weren't caused by, like, you know, the devil until probably the 19th century or so. So you don't really start to determine anything about semiconductors per se until the 19th century or so. There's a German scientist named Braun, True, in 1874 who discovered this thing called rectification. Rectification is a fundamental concept in electronics now. He had no idea what the hell was going on when he discovered it at the time. He basically he's the guy, when I make the joke about the guy with a rock and a wire, who discovered that if you have a particular kind of rock and a particular kind of wire, and you stick them together and you try and run a current through that, it goes in one direction, but it doesn't go quite as well in the other direction. That's the first thing, right? He had no idea why it happened. He wrote about it, and he published it in a journal. And that device was called, affectionately, a cat's whisker. It had absolutely no application. It was just this thing that the scientists thought was cool. So, you know, during the period of like 1850 to around 1900, there was a lot of horsing around with things which people would later understand were semiconductors. At the time, they were like, we're messing with this crystal and it has this crazy property. We can shine a light on it and it appears that there is a voltage that is evolved from this thing. What does that mean? What's a volt? I don't know. And so it was all super academic. It was all generally driven by one person who had some interest in this thing for an arbitrary or vain reason and had no application for it. And that's like, it's sort of this like dispersed view of science, right? The thing that changed all that, the first thing that changed all that was radio. Electromagnetic waves were discovered in 1888 by a man called Hertz. Hertz is probably a term that you guys have heard before. Radio was practically demonstrated by an Italian man named Marconi in 1901. And Marconi made what is by today's standards a super crude radio, which is basically a spark plug that you fired, and it made this burst of noise, which made an electrical disturbance in the air that you could pick up some amount of distance away. Initially, to pick up that thing, to pick up that signal, to transmit that signal, you used a spark plug. To pick it up, you used basically a tube that was full of iron filings called a coherer. I have no idea how a coherer works, and probably have a lot in common with the people back in the day who also had no idea how a coherer worked, but they knew it worked. Braun, the German scientist, was like, wait, I have this application for my weird cat's whisker thing, and was born crystal radio. So early radio sets used this thing called a spark gap transmitter, which was basically a spark plug. And they used this point contact diode, which was called a cat's whisker then, but it's basically this wire and a rock. And if you set the wire on the rock in just so of a way, you get your radio waves come through in such a way that you can then detect them. The spark plug sound is what became. It just so happened that this spark gap thing that was transmitting radio waves also had a lot of noise at audio frequencies, so you could hear it, which was lucky because you can't hear radio waves. So these early transmitters and receivers were the first application of semiconductor technology, although no one had any idea what the hell was going on. Enter Edison. In 1883, Edison took out a patent on, Edison discovered, he probably didn't discover, Edison's a real ass. I don't know if you guys have read much about Edison, but he was not a nice man, and he stole a lot of other people's work. So he may or may not have discovered this, but somebody around that time discovered a phenomenon similar to what Brown discovered, where you can take a couple of pieces of hot metal and in a vacuum, probably this was related to light bulb experiments, although don't quote me on that, you could get electrons to go from plate A to plate B in a vacuum. He described this as a thing called the Edison Effect and was born the vacuum tube. And this is around 1884. In 1904, the vacuum tube was applied to radio, and one thing that sucked about the cat's whisker is it was this noodly wire that was stuck on a rock, and most of the time it didn't work. And if you shook it, it didn't work. And if you moved it to a different place, it tended to not work. And sometimes it just didn't work anyway. And the nice thing about a vacuum tube is that after you made it, if it worked, it worked. Meaning, if it worked once, it was likely to work again.
Was this stuff dangerous? Did people, could you get electrocuted or shocked or?
So, the early cat's whiskers experiments, these experiments were often dangerous, yes, because they would be like, some material scientist would be like, I have a crystal and I'm going to see if it does whatever it's supposed to do better in a giant balloon full of hydrogen gas. So, lots of stupid shit like that happened and people got hurt. You didn't really see a lot of electrocution until the vacuum tube came out. Because the cat's whisker is a relatively low voltage device. And radio receivers have not very much energy associated with them. Like the goofy wire on a rock can't pass a whole lot of current. Tubes can, and they're real hot, and they're at real high voltages. So tubes are, sort of dangerous, but hey, you can't make an omelet, right? So I'm going to take a little bit of time. Although this lecture is about semiconductors, I'm going to take just the tiniest bit of time to talk about what a vacuum tube is. Because a vacuum tube is A, easy for a person to understand, and B is, anyway, the vacuum tube came about, it was useful for radio, and people were like, well, WTF, why are we ever going to use this cat's whisker again? That shit is stupid, it doesn't work very well. And now we have this new technology, which beats silicon, called the vacuum tube. So the vacuum, the microchip, as we know it, got asked out by the vacuum tube for probably 40 years while vacuum tube technology advanced. And I want to talk a little tiny bit about vacuum tubes because I think they're illustrative of the way people thought about early electronic devices. And they function in some ways similarly to the active devices that you would make out of semiconductors, and they're easier for a human to understand. Any of you who have not learned electronics but are curious about learning electronics, it's not a bad idea to start with vacuum tubes because they're A, hard to break, B, they teach economy of design, and C, they're simple to understand. D, they're cool. So anyway, a vacuum tube, right? So a vacuum tube, this is, what I'm going to draw right now is a schematic, right? And a schematic means a good way to visualize the way an electronic thing works. It's not actually, the schematic may bear some similarity to how the thing is physically built, but that's not really what you're trying to illustrate. What you're really illustrating is conceptually how this thing works. So when I draw a vacuum tube, probably most of you guys have seen a vacuum tube. So what I'm going to draw is how the electrons would think about this if electrons could think, which they can't. So the first style of vacuum tube looked kind of like this. It had that, and that, and that. So this down here, this thing is called a heater.
You're in front of it.
This thing is called a heater. This thing is called a cathode. And this thing is called an anode. For this, and this, the reason you have this circle drawn around all this stuff is because, typically speaking, these were pieces of metal and they were stuck inside this glass light bulb looking thing. Vacuum tube is called a vacuum tube because there's a vacuum inside of it. The reason you have a vacuum inside of it is so all this hot stuff doesn't burn up. Anyway, the anode has
how are they connected to the bulb or one another, or how do they inhabit the?
How do they inhabit that space? So if you have a tube, like a round cylinder, you would typically have, the cathode is this piece of foil. It's wrapped around a wire, which is like a filament of a light bulb. The filament of the light bulb is the heater. So you have this flat plate, which is wrapped around these two real skinny wires a lot of the time. Those two real skinny wires get really hot. They make the cathode really hot, and then wrapped around the outside of that is the anode or the plate. And then wrapped around all of that is this glass cylinder. Does that make sense?
Yeah, I think so.
They're vacuum sealed.
I think how it all attaches.
There's well, that's all like how good you are at glass blowing kind of stuff. And so typically, I think, you started by poking these wires through the bottom of this tube and pinching it, and then you would extract the air through the top, which is why if you look at a vacuum tube, there's a little loop, there's a little hat on the top of a lot of vacuum tubes, which is where you pulled a vacuum on it and then pinched it off. There are some great videos on YouTube about like old men making vacuum tubes, and you should check it out because they're awesome. But I'm sure there's a ton of history of how they get made. I don't know it that well. Anyway, so you have, this is a diode. You have a heater, a cathode, and an anode. Cathode and anode are terms that you'll see all the time getting used in technology. What they mean is, cathode means thing that's negative, anode means thing that's positive. So in a rectifier like this, you would, or in a diode like this, what you would basically do is apply some ton of current to this heater, which you would do through a battery or through a generator or something. You would apply a signal to the cathode, and if you had a waveform that looked like, you know how it's like, if you guys don't understand what voltage and current and stuff means, you should ask. I meant that. So if you get real lost now, you'll get lost later probably. So the cool thing about a diode is if you look at the power coming out of your wall then and now, you'll see this thing that looks like a sine wave, sort of, where this axis is voltage and this axis is time. If you apply that to the cathode of this device, what you will see at the output is this. Meaning that only the positive parts of that wave come through. Why is that important, you say? It's important because it's important for a bunch of reasons. One of them in radio is rectifying the radio wave. Rectifying means taking a thing which goes above and below zero, if you call this line zero, and making it into something which only goes above or below zero. You can't hear a radio wave. This is fundamentally important in trying to listen to something you can't hear. A, and B, it's important for turning power that comes out of the wall into the kind of power that most devices use. It's useful for turning AC power into DC power. So That's a vacuum tube. There was this enormous development in 1904 which changed the game, which was somebody figured out how to put a third contact in here. A lot of the time when you talk about contacts in vacuum tubes, you don't talk about the heater. The heater is this thing which was hated on by people for a million years and which was a huge push for developing the semiconductor, because it's basically like a light bulb that you have to stick inside anything that you want to do any electrical work. So if you have a device with one of these in it, you need to supply enough power to run a ton of lights inside it, essentially. Plus they get hot and they burn you and they burn the device up. So generally, we hate heaters. So people figured out how to put a third electrode inside this thing, which is called a grid. And this is where things get really exciting. This is where you get the first active device. And an active device in electronics world means something that you can get a bigger signal out of than you put into it. It's a thing that has gain. More specifically, it has power gain. There's another kind of device called a transformer, which is a bunch of coils of wire that you wrap together, and you can put voltage A into one side and get a higher voltage out of the other side, but you don't get any more juice out of one side than you put into the other side. Good.
What's juice?
Juice in this case is power. I used an evocative term there instead of a technical one because I didn't want to lose anybody. But in a transformer, you can change voltage A to voltage B based on the number of coils that are in it. But if you put a watt into one side, you will never get more than a watt out of the other side.
Could you explain voltage?
I can try. So the most fundamental prayer to all electronics nerds is this thing called Ohm's law. Ohm's law is V equals IR. Voltage equals current times resistance. All of those are sort of the most fundamental. They're derived from this really hard set of equations called Maxwell's equations that a very smart man made a long time ago. And the difference between a scientist and an engineer is that a scientist cares about Maxwell's equations and an engineer just needs to worry about V equals IR. And voltage, in a nutshell, one reason why it's hard to describe voltage is there's a history of people making terrible explanations about what voltage is. You hear it described a lot of the time in terms of water and water pressure and like, you know, a hose versus a squirt gun, and all those explanations are shitty, I think. However, they are things that most people understand, so they still get used a ton of the time. Voltage is essentially, is it okay with everyone if I use the term electron? Is that cool?
Yeah.
Okay.
Can you explain the term electron?
Can
you show us one?
Heretic. Voltage essentially, also in describing this, equally wrong is to anthropomorphize these forces and fields, which I'm just about to do. Voltage is essentially how bad an electron wants to get from one point to another point. A classic example of voltage is when you stuff your feet on a carpet or rub like a balloon on your head and then touch something else and a spark comes out. Generating a spark is a lot of voltage. It's thousands and thousands of volts when you do that. Anytime you see a spark jump through the air, it's a ton of voltage. However, no one ever gets really hurt by that. Like your cat gets annoyed when you touch his ear, but like, but he doesn't die. Enter the I part of V equals IR, which is current. Current is sort of like current is like how many electrons are going from point A to point B. In the shitty water analogy that you all go home and forget, current is often described as the diameter of a pipe, right? Like water pressure is described as voltage. Diameter of a pipe is described as current, and the two of them multiplied together is how much electricity is going from point A to point B. That's power. Resistance is how difficult it is for those electrons to go from point A to point B. If V equals IR from algebra, V over R equals I. Is that right? V over R equals I. Or V over I equals R. So voltage over current equals resistance, which says if I have a lot of current and not very much voltage, then I must have a very low resistance because I don't have a lot opposing that flow of electricity. Does that sort of make sense? Okay. It's how bad electricity wants to get from point A to point B. Another thing that sucks about the vacuum tube, or sucked for a lot of people for a long time, was that it takes relatively high voltages to make it work. High voltages like to travel across things like air and people, so high voltages in general are more dangerous. So vacuum tubes essentially they were made out of glass, they broke a lot, they were hot, and they were dangerous. They had this thing called a grid in them, though, around 1906, and we were probably way behind for getting to semiconductors, which allowed you to do this thing where with a very small voltage here on the grid, you could change the amount of current that was flowing from the cathode to the anode. You can make a wiggle here at the grid of this device, which was maybe 1 volt big. And you could get a wiggle, with some other stuff hooked up to this, you could get a wiggle out at the anode, which was maybe 50, 60 volts big. Which means that you could take a small signal, like a radio signal that's been transmitted a really long way, and you could amplify it. All of a sudden, this made it possible to transmit signals really long distances. It made it possible to have stereos and hi-fis. You could have a tiny signal that was coming off a vinyl record, and you could put it through a couple of these, and you could have it drive a loudspeaker. This had industrial applications. It had tons of musical applications. It had commercial applications, and it was super important. The important things for true dorks in the audience, one thing that's important about the vacuum tube electrically is that the distances between these things are really big. You can see them with your eyeball. And in electronics, if you can see a distance with your eyeball, it's enormous. The other thing that's really important is that this control voltage here at the grid is negative. So if you ground the cathode, if you don't get this part, we're just going to move on. If you ground the cathode and you have a voltage that's -1 volt to 0, that's the sort of wiggle that you're looking for to make this thing work, with anode being particularly positive. Meaning your grid, your control port doesn't go positive, it goes negative. Finally, the control voltage that goes in here, there's no resistive connection from the grid to the cathode to the anode generally, which means no current is drawn by the grid, which is another really important thing. So you can put whatever ethereal voltage into the grid and get something less effete and ethereal out. That's the vacuum tube. Later on, people added more and more of these weird grids to the vacuum tube to get different weird esoteric effects, get higher frequency operation, and the vacuum tube, people still use vacuum tubes, not much today, but the vacuum tube didn't really reach peak sales until the 60s or 70s, well into the era where semiconductors were commonly used. So it's important. All right. Vacuum tube digression over with. So nobody cared about semiconductors at all in any way other than an academic one until World War II. World War II came around, and it was important for technological reasons, for lots of reasons which everyone in this room is aware about. But for our little lecture, we're going to talk specifically about radar. All of a sudden, people knew about this mysterious thing called radar before the 40s. Once the 40s came around, they became really interested in making it work right. And you found